Okay, so this is centripetal acceleration. What it is the acceleration of any object that is moving around in a circle. So one object that is constantly experiencing this is the space station, because it is moving about the Earth in a constant circular motion where its velocity at any point in time is tangent, which, if some of you might remember from earlier in the semester, tangent lines were like any sort of point you can pick on a curved object and just draw a straight line from that point. That means it is tangent to the circle. It's just a definition. Okay? So, what this actually is if you've ever been in one of those spinny, like dizzying, horrible rides at roller coaster theme parks that just are there to make you puke. I hate them because I get really bad motion sickness and will puke. But it's the basic force that keeps you from flying out of that object. It's the idea that when you're spinning around, you are being pulled by a force inward. Even though it feels like you're being compressed, you're actually being forced inwards towards the center of whatever is spinning. In this case, the Earth has an acceleration that is known as gravity, which we know is 9.8, that is always pulling the space station towards itself. If it is able to go fast enough, it will be able to maintain this perfect circular motion and not get pulled in by Earth's gravitational force. Same idea if you've ever spun a water bucket around your head, which I will show a demonstration of, not me doing it because I am moving and I don't have any water buckets available, but I will do it in the future, trust me. If you spin it around, you'll notice the water stays inside the bucket, and it is all thanks to this wonderful rule of physics. This formula for centripetal acceleration means centripetal acceleration is equal to the tangential velocity, so whatever this velocity is right here, divided by the radius. Okay, we're going to go ahead and move on. I know that was a bit rambly, but I think we got the general gist of it. Okay, so let's do an actual practice problem with this. We'll still use the guess method because good old guess method never lets us down. A tire on your cousin's lifted up Cadillac has a radius of 1 meter, so r is equal to 1. If it turns with a velocity of 6 meters per second, so since this is a wheel and it's spinning, we know this means the vt, so the tangential velocity. What is its centripetal acceleration? So instead of just writing a, we write ac, just to note that little c tells us it is a centripetal acceleration. So that is our unknown. Okay. R is equal to 1. Vt is equal to 6. Acceleration is our unknown. Our equation for anything that has these three values is AC is equal to Vt squared divided by R. And now all we gotta do is plug it in, and we'll get AC is equal to 6 squared over 1, which we can even check the units. Meters, that's meters per second squared divided by meters. So we will get 36 meters squared over second squared divided by 1 meter. That 1 meter cancels out the 2 up there. 36 divided by 1 is still itself. So now we're left with units for acceleration, which are meters per second squared. And that is our answer. Now we're going to go into one more problem, but this time it's going to be focused around solving for something else. So our next problem, like I was saying, we will have to solve for other things every once in a while. So centripetal acceleration is what we're looking for. If you've ever been to Six Flags Over Texas in Arlington, which is not too far away, you'll know what I'm talking about. The Shockwave is a loop-de-loop roller coaster. It's got 2 big loops. That's it, and you're done. But it's still fun. So you decide, you know what? I'm going to go on the Shockwave with some friends. You somehow were told right beforehand that the centripetal acceleration that you experience in the loop is this value, 27.6 meters per second squared. If the loop has a radius of 26 meters, that's my R, how fast are you traveling? How fast are you traveling? That means that is VT. Because we're traveling in a circle, that must mean VT, not any other type of V, okay? It needs to be consistent. So AC is equal to 27.6 meters per second squared. Our radius is equal to 26 meters. The only equation we know that has these 3 things exactly as they are is AC is equal to VT squared divided by R. Now if we plug things in, we got 27.6 is equal to VT squared divided by 26. In order to get 26 to the other side, we need to multiply 26 on this side to cancel it out. What we do to one side, we gotta do to the other. So 27.6 times 26 is 718.24. Okay? So 27.6 times that is equal to VT squared. We square root it to get rid of that square, and we will be left with an answer of VT is equal to 26.8 meters per second. That's it. Not too hard. The trickiest thing is making sure you don't accidentally plug in this value to VT, or you don't accidentally forget to square root something, or you just make a silly algebra mistake, which happens. We're human, right? But now there's some practice problems, and we'll talk about our next part of acceleration, or centripetal acceleration, which is this. Weird. For whatever reason, we haven't really talked about what happens if you let go of something, right? So if I'm spinning this circle around, this little ball around in a circle, and it's going clockwise, which if any of you are ever confused about clockwise, it's the direction that the hands move. If you ever look at a clock, you can look at one in your room, my room, whatever. For whatever reason you're in my room, I don't know. Maybe you're actually at school. Maybe you found my house. That would be weird. Anywho, weird tangent aside, if I were to let go of this object right here, what would happen would be the ball would continue in a perfectly straight line. So I can let go of the ball here. It would travel in a perfectly straight line of whatever the VT is. If I were to let go of it anywhere, it will continue in a perfectly straight line. You can actually test this yourself by spinning something and letting go. Be careful, don't do it in the house. Actually, I take all that back. Don't do this and get in trouble and then blame me. It's not my fault. Totally on you if you break something, okay? All right. So we know objects must travel in a straight line. And the centripetal acceleration is always directed inward towards the center, right? Always directed this way. So if I were to do the ball at any other point, like let's say the ball's right here, the acceleration would be directed that way, okay? And the VT would continue in this direction. Here's how I know this is true. So the way a hammer throw works, it's an Olympic event, is they literally try to build up as much speed and build up as much centripetal acceleration as possible. And then they let go of it. You'll notice she lets go of it right as her hand is directed at that opening, and that's why the hammer throw flies that way. But this one's a little hard to see, so why not we try something else? How about a softball? So you can actually see her arm is going to travel in a circular direction like that. The ball is still in her hand, and it's let go right here, and the ball travels in a perfectly straight line. It starts dipping down, but that's because she added some spin to it. But you can see it leaves the camera in this direction, straight. Last one that also really shows this off perfectly well with a bit of slapstick. Look where she lets go of it. She lets go of it when the hammer is still over there. That causes the hammer to go perfectly that way, and it is why you should never stand this close to a track star, especially one that is in high school, like this person pretty much probably is. Hopefully that guy can still have kids at the future point if he wants to, but I'm not holding my breath. Hopefully you understand what happened is if that ball was let go like a half second, quarter of a second later, it would have been perfectly fine. But because she let go of it right then, it traveled in a straight line directly to that guy's crotch. Fun times in physics, right? Okay, now do the next practice problem, get done with everything, and you're pretty much good to go. Okay? I'll have a review at the end for all the practice problems if you want to look through, check your work. And yeah, that's it. Have a good one.